Good afternoon. We're going to talk about quantum computation. This morning that I talked about classical computation, I thought that since there were no questions in the lecture, I thought maybe what I had said was a little bit difficult to raise any question. Then from the questions that were asked after the lecture, I found that maybe it has been too trivial to raise any questions. So I decided to add something to the end of my slides to make it probably up to the level of the students here. Okay. We learned about Turing machine. Once again, this is the tape. And here you have bits, zeros and ones. We call them bit, classical bit. Here you have the brain of the machine, which is the collection of the states. Here is the head. And this is the working of the machine, the transition functions. In which state you are, what you read, and then you decide what to write, your state of mind and the brain of the computer changes, and then you decide to go right or left. This is all that we know from classical computation. And then we have the Church-Turing thesis, which says that if nature works according to classical, then there is no machine more powerful than Turing machine. This is the Church-Turing thesis. It has not been proved because it's not a theory, but has been checked over and over again over the last 8 years. And, but in 1985, David Deutsch came in with this idea. Nature works according to quantum, not classical. Right? All the Church-Turing thesis is based on classical physics. You have particles, you have positions, you have certainty, you have determinism, as Angelo showed us. But nature is not classical. Nature is quantum mechanical. Atoms, photons, electrons, all these things behave quantum mechanically. They do not have different positions or momenta. They have waves, they have superpositions, and so on. So maybe we can have quantum Turing machines. And maybe we can go back and reconsider the David Hilbert. So, we have a Turing machine, which is the classical one. But instead of 0 and 1 on this tape, instead of bits, now you have qubits. Because each element in each of these cells, that's not just 0 or 1. It can be a superposition of it. This is quantum mechanics. And then, the head of the Turing machine doesn't go right or left. Maybe it goes into a superposition of left and right. Because nature is quantum mechanics. It's not classical. And more than that, the brain of the Turing machine, the states of the Turing machine are not defined, are not deterministic. Maybe the Turing machine brain is in a superposition of states, not just one state. This means that at any instant of time, the Turing machine, the Turing head, is in a superposition of all the cells. So maybe you have a much, much, much more powerful than the classical Turing machine. This is the idea. And since it's difficult to imagine the working of such a machine, then you can prove, and it has been proved, that its working is equivalent to a second In the same way that the classical Turing machine could be simulated by a classical circuit, the Turing machine can also be simulated by a quantum circuit. By a quantum circuit, we mean that we have a state, a quantum state, here, side. It is a superposition of all these qubits on the tape. Here our tape is finite. And then the huge quantum circuit transforms this state into another state, which we want. So this is the computation that the Turing machine is doing. There is a quantum circuit, a huge state comes in, and a huge state goes out, and this is the solution of it. And this is the quantum circuit. Inside the quantum circuit, there's a huge collection of gates, quantum gates. Instead of classical gates, which were and, or, not, and so on, now you have quantum gates. Quantum gates is just a small unitary operator. These are small unitary operators, X gate, Y gate, Z gate, and Pauli gates, or some other rotations around different axes, and some two-dimensional or gates which act on two qubits, which we call CNOT gate. And they are important because if it's not for these gates, then every qubit is doing independently, which is not what we want. We want that the qubits interact with each other, talk with each other, and that's why we need these CNOT gates. So any quantum circuit, any huge quantum unitary operator can be constructed by a combination of these gates, the single qubit gates, and these CNOT gates. You can prove this. Any huge unitary operator can be combined and reconstructed by the addition of suitable unitary gates on one qubits and CNOT gates. Some of these gates are like this. This is the X gate. These are the Pauli operators. The Pauli operator, as you see, it switches 0 and 1. The Z1 gate, which is again a Pauli operator, it gives a phase, 1 or minus 1, depending on which one is written on the cell. Where 0 bit does nothing, where 1 bit, 1 qubit in the state of 1, it produces a minus 1 phase. And this is called a T gate, and so on and so on. And this is the CNOT. CNOT is an abbreviation for the control NOT. It means that if this upper qubit is in the state 0, it does nothing, it acts like 1. And if the upper qubit is in the state 1, it acts like NOT, or X gate. That's why we call it control NOT. It is controlled, the action of this gate on the second qubit is controlled by the status of the upper qubit. That's why we call it control NOT. So any quantum gate, any quantum circuit, no matter how complicated, can be constructed from these gates. And then we can ask, we have made a lot of progress from classical Turing machine to quantum Turing machine, because now the quantum Turing machine can be a superposition of the states of mind, superposition of the states of the head, superposition of the qubits on the tape, and it's completely imaginable that it could be much, much more powerful than the classical Turing machine. So we ask, is a quantum computer more powerful than a Turing machine? By more powerful, we mean that can be solved problems by a quantum Turing machine which we cannot solve by a classical Turing machine, right? We showed that by a classical Turing machine, we can solve or we can formulate any algorithm, any classical algorithm, right? Any problem that can be solved by algorithms can be solved by the Turing machine. No BS. Is quantum computing more powerful than classical computing? Is there any problem which we cannot solve by classical Turing machine, but we can solve by quantum or by quantum computing? By quantum Turing machine, I mean the same as quantum computing. What is the answer? Yes. The answer is yes. No. No. You can vote. Yes. Yes. Or no? Yes.
We should define what more powerful means.
But the same thing that I told you. It can be had problems that quantum Turing machine can solve, but classical Turing machines, no, they cannot. And the answer is no. It has been proven that it's not possible. And quantum Turing machine or quantum computers are not more powerful than classical computers, in the sense that it was just said in endurance. There is no problem that quantum computers can solve what classical computers can. Right? It has been proved rigorously. But the idea of the proof is this, that after all, what a quantum computer does is a series of algebraic equations. Right? You give it a state, like psi, and it does some operations, some unitary operations, some big metrics. And this big metrics acts on these initial states. It's a linear algebraic function, and produces another state, which is the state on the table. Right? It's just the same thing. And something like that, like this. This is the initial state, right? The amplitude of the states on the Turing tape. This is the unitary operator. It doesn't matter that how big it is. In principle, what a computer is doing is this. It turns a state into another state. And since, after all these states are just, all these probabilities, all these amplitudes are just complex numbers. A complex number is a pair of real numbers. A pair of real numbers can be written as a sequence of zeros and ones. So what a quantum computer is doing is actually doing this computation, right? It are, for example, these side 1, side 2, side 3, and this computation is just the computation in the first row, the computation in the second row, and so on and so forth. So what really quantum computing is doing is just a linear set of calculations, right? If this is the case, then we can go back to the question of David Hilbert. The fundamental question of David Hilbert, steel has a negative. So this is good news. It means that there's a steel space for your getting the Nobel Prize, or a Fields Medal, or proving a theorem, and so on and so forth. There is no reason to be disappointed by conventional quantum, right? If this is the case, then we can ask the question, is a quantum computer faster than a Turing machine? It was not more powerful, right? But it is faster. Yes, please.
Can I ask a question related to the previous question, not
Yes.
this one? So, was the proof of equivalence related to a realistic quantum computer or to an ideal quantum computer?
No, the idea.
But perhaps I'm too naive, but in an ideal quantum computer, you can, with superpositions, you can encode precisely a real number, which has infinite digits.
Yes. Yes, but after all, even in a real quantum computer, you have errors.
No, but I'm talking about the ideal one.
No, there is no ideal quantum computer.
No.
No?
But for mathematical proofs, there could be.
Yes, yeah. But then, you can have a very long Turing machine with any precision that you want. Right? You just use a longer tape or multi-tape to increase your superposition as much as you can.
Okay.
Right? So, the question is a quantum computer faster than a classical computer? And the answer is yes, extremely and unimaginable. It's extremely fast. And that's the real advantage of quantum computing. It's not more powerful in the previous sense, it's more powerful in this sense. It's much faster. And why quantum computers can be so fast? Exactly because of superposition. Because at any instant, a quantum computer can be in a superposition of states, and the superposition of states is exponential superposition of states. Because if you have, for example, 10 qubits, these 10 qubits can be in a superposition of 2 to the power of 10 states. 10 to the power of 10 is 1024 states. So you just add 1 qubit, and then you double the number of states that the quantum computer can be in. That's why it's very difficult to increase the number of qubits. But if you add the number of qubits, it means that the space of qubits, the space of possibilities, increases exponentially. If you have one classical computer, for example, a classical computer of 100 bits, right? Then you want to do a calculation, calculating a function, f of x, right? You give the variable x1 here. It calculates for you the function f of x. Suppose that you want to do it for another value. Then you use your classical computer once again, right? You give the computer the variable x2. It produces the function f of x. Then you give it the variable x3. It produces f of x, and so on and so forth. So if you want to evaluate the function of f of x for a large number of inputs, you have to run the classical computer many, many times, right? If you have one classical computer. If you have many classical computers of 100 bits, suppose that you have many laptops, then you divide the jobs between these laptops and you do a parallel processing. So you make all these computers to run in parallel and calculate all these variables, all these functions for all these variables simultaneously. This is what really is being done in classical computers. You make parallel processing. All these computers are doing parallel processing. But if you have only one computer, one quantum computer of 100 qubits, then this quantum computer is simultaneously in 2 to the power of 100 states. 2 to the power of 100 means 10 to the power of 13. It's a huge number. So simultaneously, this quantum computer is in a superposition of 10 to the power of 30 states. And it can do for you quantum parallel computation. It means simultaneously calculates all these f of x. So you give the superposition of all these variables at once to the input of the quantum computer. It produces the superposition of all these f of x. Right? Of course, you have to be smart to ask the right questions. Right? Preparation of this superposition is easy, and you can look at the output, and at the output you can measure the output. And when you measure the output, because of the probability, because of the collapse, you obtain only one of these f of x, not all of them. So it means that quantum parallel processing is extremely powerful, but you have to be clever to ask the right question. Because at each instant of time, due to the collapse of the wave function, you only obtain one of these effects, right? So let's see what kind of question we can ask. Before going to that, let's once again, see the power of or the advantage of quantum computers. This is a classical computer. We do not have anything like quantum information or quantum data. Everything that we have is classical. We have classical data, we have classical problems, classical numbers. We give this to a computer, and the output is again classical. It's not quantum. You read the output either on the monitor or on the paper or anything. So the input is classical, the output is classical. This is the situation with the classical computer. It has a very small stomach to digest this data and produce the answer. On the other hand, this is the situation with quantum computer. You again give classical input, the same classical. You again find the same classical output, but the stomach of the quantum computer is extremely huge and it can process all this data extremely fast. That's the advantage of quantum computing. So let's see an example of quantum algorithm. I repeat that when you give a uniform superposition of input states, uniform superposition of x1 plus x2 plus x3, the output is a superposition of f of x1 and f of x2 and f of x3 and so on. So you do not have access to all f of x's. You do not have the access to all the outputs. When you measure one of these f of x comes up, and it doesn't mean really a huge advantage. But you have to ask the right question. So let's see. People have tried to formulate problems, to formulate quantum algorithms, which gives you this advantage. If you ask, if you want to delegate a simple question to the quantum computer, you may not get any advantage. So, I'll give you an example of quantum search, and I'll give you the idea why this quantum search is successful in quantum computing. Suppose that you have a big database, right? The size of the database is n. For example, it can be a sequence of genes, and you want to find a specific item here, right? Which has a specific property. The best classical algorithm is O of n, of the order of n. Remember that this database doesn't have any structure. It's not ordered alphabetically. It's not ordered in any sense. So the best thing that you can do is to do blind search. If you are lucky, the data that you are looking for, it will be the first one. If you are unlucky, it will be the last one. So on the average, you have to search this database the number of n over 2, right? On the average. It's on the order of n, the best classical algorithm. So let's see what we can do with quantum computing. With a quantum computer, you can do it square root of n. It's a huge advantage because suppose that n is, for example, 1 million, right? Then you reduce 1 million to just 1,000. It means that you save 900,000 plus 90,000 and so on. You save everything. And as n increases, you save more and more and more. How? How this is possible? The basic idea of any search. Note that we are talking about a serious search problem, right? We do not look at, for example, searching for emails or passwords or addresses and so on. We are looking for a serious scientific problem. In cosmology, in astrophysics, in biology, in physics, you want to find the ground state of some complicated physical problems and so on and so on. Any problem, any search problem, can be formulated in this way. You have a huge database, the elements of which are called X. For all of these X, which do not have that specific property, f of x is equal to 0. For that specific property, f of x is equal to 1. So we name this specific gene or specific item W, f of W is equal to 1. But All the other ones are called x, x1, x2, x3, and f of x is equal to 0. And we want to find W. What is W? Right? Which W has this property? Whose f of W is equal to 1. Any such problem can be formulated in this abstract. So let's see how we can go about this problem. First of all, we read the function f of x. You give the uniform superposition to this function, to this quantum quantity. With a little bit of trick, you can formulate a problem where you can construct a circuit, this quantum circuit, so that f of x goes to the exponent of this maximum. So the output is not f of x, is minus 1 to the power f of x. This is the trick of these quantum gates. You can manage to construct a circuit so that the output is minus 1 to the power f of x. Right? So let's see what happens. We give the uniform superposition. This is a symbol for the uniform superposition. Right? All of these x or w's have equal amplitudes. Right? All the amplitudes are the same. This enters the function. We read the function once. Right? We ask which x or which w has the value f of x equal to 1. We are asking this question. What is the output? The output is this, right? Because minus 1 to the 0 is 1. Minus 1 to 1 is minus 1, right? So the amplitude of W is minus 1. The amplitude of all the other states are 1, right? And W is found. You believe? Who believes in this argument? Who doesn't believe that we have done the job? We measure this, we measure the output, and we find the W. Who's skeptical about this? Angela is skeptical, but Angela is an expert. But how about you? Do you believe this? Do you think that we have succeeded in finding W? We measure the output, and we find the W. You are skeptical, right? Why?
Maybe they can take it to the shared time. Well, we're not certain.
No, you have to think about the probabilities, right? What is the probability of finding distance? Is the probability of this one different from this one? No, because the probability is the amplitude squared. So there is no difference between this W and this. You obtain them by equal probability, right? Because the probability in quantum mechanics is the square of the amplitude. So there is no use at this stage, right? So what you do, at this stage, you design a quantum computer, a quantum circuit, right? The next stage, which does this wonderful thing. It averages all these states with respect, it inverts all the amplitude with respect to the average. Do you believe that the average of all these amplitudes is this yellow line? Do you believe that? Believe that. Because one of these is negative, all the others are positive, so the average is a little bit lower than 1. It's, for example, 0.99 because of this maximum. This is the average. Now this circuit inverts all these amplitudes with respect to this average. Think of this yellow line as a mirror. The tip of all these up arrows becomes below the mirror, right? If you look at this. And this tip goes here. So the output is something like this. Do you believe this? This is the action of this mirror, right? Now at this stage, if you measure the output, the probability of finding W is higher than the probability of the others. But note that all the others, their number is huge. W is only 1, but the others are many. So still, there is little probability to find W, because W has many rivals. All of these have probability of being found in your calculation, in your measurement, right? The probability of each of them is low, but there are many of these x's. So you have to repeat this. We repeat this, right? We give it to the function, to the circuit, which calculates W, and again, this happens, right? Again, W, because f of W is -1, becomes here, and then, again, we take the average. The average now a little bit lower. Our mirror has become lower, and then after inversion, this is the inversion. Inversion will be up above the average, and this should be corrected. After inversion, you have this probability for W, and these probabilities for X's. Note the chance of finding W is higher, but you have to repeat this. And then if you do this calculation, it's a 2-page calculation or a 3-page calculation, you will find that after O of the square root of n times, the probability of finding W is much, much, much higher than the probability of the others. And you can find them. So you measure the output and W pops up. This is the quantum search algorithms, right? Which has a huge advantage. And why quantum search is important? Because actually no real problem, so to say, no difficult real problem can be solved by analytical argument. All hard and difficult problems, which we do not have any analytical argument for that, should be found by search. Protein folding problem, ground state of Hamiltonian, optimization problems, and so on and so forth. They should be solved by brute force approach. So, now we can ask. Angelo talked about probability. In view of the probabilistic nature of the quantum mechanics, because when you measure, you obtain something by probability, by chance. Right? What kind of problems can be solved by a quantum computer? Suppose that you give 2 numbers to quantum computer, and you want the addition of these 2 numbers. You give 2 and 3, with the probability it gives you 5, with the probability it gives you 6, with the probability it gives you 1,000. This is quantum computing. So you have to ask the right questions and formulate the right algorithm. So the problems that we can solve by quantum computers are these problems. It can be formulated this way. Problems which are difficult to solve, but easy to verify. Right? Problems which can be coded as finding a needle in a haystack. If you have a haystack, and there's one needle in it, right, which is the right answer to the question. Somebody, finding the needle is quite difficult. But if I find the needle and give you, this is the needle, you can verify this. Easily verify this, right? This is the problem that we can solve by quantum computers. If somebody asks you, what is the shortest haystack, what is the shortest hay in this haystack? It's very difficult. Nobody can verify this. But this type of problem, which are many, can be solved by quantum computers. If you write the correct quantum algorithm. But note that we do not have developed in the last 100 years enough intuition to be at ease with quantum phenomena, with quantum concept, with superposition, with entanglement, with circuits and so on. So it takes a long time, so that our students and us get used to quantum language, quantum concepts, so that we can write quantum algorithms easily, and we can develop our intuition. It takes time. Up to now, people have tried to, and have succeeded to, find quantum algorithm for a specific finite set of problems. Not difficult. For example, factoring large numbers. We have a very successful quantum algorithm program. If you give the best classical algorithm to the best classical computers that we have now, for example, these supercomputers, if you give, for example, a number which is 600 digits to solve, it takes billions of years, the age of the universe. But the quantum computer can solve it in a matter of months if it's constant. So factoring is a number. Again, it's one of those problems which you cannot find the answer. But if somebody finds the answer, you can verify it. You give me n, which is a very large number, I give you the factors. You multiply the factors, immediately you find that my answer is correct or not. If it's not correct, if the probability is that it's a wrong answer, you repeat the algorithm and you find the answer. Factoring is one of these problems. Finding x in this equation. This is a linear set of equations. Ax equal to b. Right? We want to find x. Again, this problem has been solved by quantum computers. Find s in b in this equation. This is called discrete logarithms. We have two numbers, b and a, and we want to find s such that a to the power s is equal to b. These are all integers, and all these exponentials are mod n. We want to find s. Again, this problem has been solved. And finally, I give you three matrices, A, B, and C, and ask if A times B is equal to C or not. These are some of these problems which have been solved by quantum computers in the field. Now, this is the material which I have added this morning, at lunchtime, to keep up with your lab. There are other forms of quantum computation models. Quantum circuit is one of them. The basic theory is quantum Turing machine, superposition, and so on and so forth. But then you can construct different models for this. One model was quantum circuit, right? You have gates, you input the states, and you measure the output. But there are other ways. One of them is the adiabatic quantum computation. You all know the adiabatic quantum theorem, adiabatic theorem in quantum mechanics. If you smoothly change the Hamiltonian, the parameters of Hamiltonian, the ground state smoothly changes and adapts itself to the ground state of the new Hamiltonian, right? Many things change, but the ground state smoothly changes and becomes the ground state of the new Hamiltonian, provided that you do these changes slowly. This is the adiabatic theorem. Now let's introduce a very important problem. This is called satisfiability problem. And in computer science, you can call it the mother of all other problems. It's very important. Why it's called the mother of all other problems? In technical terminology, it's called an NP-complete. NP-complete. Why this? Let's first describe the problem, and then I come back to this question. These S1, S2, S3, and so forth, they are just logical bits, right? 0 or 1, true or false, right? And this is the symbol for OR operation, logical OR. This is the symbol for AND operation in logic. And what is this symbol? Who guesses? Not. And this is the logical operation. S1 or S2 or S3, and S2 or S3 bar or S4. Right? We have 4 logical values, S1, S2, S3, and S4, which are true or false. And we have made a simple function, f of S1, S2, S3, and S4. And the expression is this. Now we ask, the question is this. Is there any value true or false of S1, S2, S3, and S4, so that it makes this f as a true logical value? Is there any value of these logical variables which make this f to become true? Right? That's why it's called satisfiability problem. Are there any S1, S2, and S3 variables and S4 so that it satisfies? Can you guess some of these? For example, I can make S1 equal to 1, true. Then this one will be equal to 2. And then, because there is an AND here, both of these expressions should be true, right? Because we have an AND here. Do you agree? We have to have AND here. So both of these should be true. And for that, for example, I can take S1 equal to 1 and S3 equal to 1. Right? It's solved. How about S3 equal to 1? If I take S3 equal to 1, this will be equal to 1, but this one will be equal to 0, then it depends on the value of S2 and S4. So I have to check, right? But this one was simple because the expressions were simple. But you can imagine of very complicated functions, right? So, among all these satisfiability problems, one problem is important. It's called tree-satisfiability problems, or tree-sat. What it means, tree-sat? It means that all these expressions are a combination of three values. All these, so to say, clauses are three values. That's why it's called tree-sat. So why this problem is important? Why people should be interested in this, so to say, trivial problem? Why? Right? This is one of the most important problems in computer science, right? And it is the first important problem in computer science. It was proved in 1970 that if somebody solved this problem, all the other problems of computer science can be solved easily, right? So every problem of computer science is reduced to this problem. It's mapped to this problem. That's why it's important. This problem is important. The tree-sat is important. Why it's called the mother of all problems. Of course, there are some technical terms which I ignored, right? But the idea is correct. The tree-sat problem is the mother of all problems. It's an NP-complete problem. So is it possible to solve this problem by quantum computers? By adiabatic quantum computation, you have the idea how to solve this problem, or at least how to go about solving this problem. According to the problem of conservation of difficulty, the difficulty goes to somewhere else, but this is the idea. Suppose that I have a Hamiltonian, it changes by some variables, and the ground state of this Hamiltonian is something like this big value of ground state. And I start, suppose that if I write the Hamiltonian so that the true ground state of this Hamiltonian belongs to this solution, right? According to f, according to the function that you give me, I construct the variable Hamiltonian, and then I start from somewhere, and the physical principle of the system goes to this ground state, and you find a solution. Let's go into a bit more detail. I start from a single Hamiltonian, right? Whose ground state I know. Ground state is unique. I know the ground state, the system is here. The physical system is here. Then I change gradually the parameter of the Hamiltonian so that the Hamiltonian becomes this one, which corresponds to this function, which I wrote here, right? The function is complicated. The function is, the Hamiltonian is something like this. 1 minus s h0, which is the simple Hamiltonian that we have, plus hp, which is the Hamiltonian, which is defined from that function. I do know the function, but I do not know this ground state. If I change slightly the Hamiltonian, slowly the Hamiltonian, the ground state, this ball moves from here to here. And then I measure this position of the ball, I measure the ground state, I measure the value of the expressions. How to go about finding this solution? Suppose that the expression is something like this, the same expression that they wrote. f of S1 is S2. What is it? We have two clauses. For each clause, I write the Hamiltonian, small Hamiltonian, sorry. H1 plus H2. H1 is for this one, H2 is for this. And then, in view of this S1, S2, and S3, I write the Hamiltonian this way. Note that if Z1, Z2, and Z3, if S1, S2, and S3 are equal to 1, all of them are equal to 1, then this H1, if any of them are 1, if any of them is true, this H1 is equal to 0. Right? It goes to the ground state. The ground state energy of H1 is 0. If any one of them, of these variables is 1, right? Any one. Due exactly to this O. How about this one? For this one, H2 is something like this. Note that this plus sign is in view of this not here. If any one of them is 1, if S2 is 1, this is 0. If S3 is 0 or minus 1, this is 0. So H2 will be in the ground state. And the whole Hamiltonian is this. So I gather a lot of qubits, and then I construct this Hamiltonian. Because I know the function, I can construct this Hamiltonian. I manage to tune the coupling so that the Hamiltonian is like this one. Then I start from H0, which has a very simple ground state. The ground state of this Hamiltonian is a Hamiltonian of set of spins in the x direction, a magnetic field in the x direction, as this Hamiltonian, and size is something like this. And then HP is not something like this. And then gradually, when I move this Hamiltonian from H0 to HP, the ground state, which was the simple one, produces the solution of this expression that I didn't know. This is the adiabatic quantum computation. Of course, it's not easy to implement this because the adiabatic theorem is guaranteed to be true when the energy gap doesn't become too small. If it becomes too small, then you have to proceed much more slow. But this is the idea of adiabatic quantum computation. Another model of quantum computation is topological quantum computation, for you to be familiar with. I just tell you the basic idea. There are many sources of errors in quantum computation. I will talk about quantum errors in 2 consecutive sessions, perhaps the day after tomorrow. Quantum errors are very delicate. Unlike classical errors, quantum computers are extremely fragile due to the errors in the environment. I will tell you about that. There's an idea with lots of investment by big companies to develop topological quantum computations. Those who are interested in, for example, mathematics or these kind of things can think about studying and learning topological quantum computation. The idea is that since topology is insensitive to small changes, right? Anything that is topology is insensitive to small changes that may occur. For example, the topology of a sphere is the same as the topology of the watermelon, ellipsoid, and so on. That's the basic idea. Of course, the everyday life word for topology is this. But the topology technically means that some global characteristic which are insensitive to details. So one of the basic idea of topological quantum computation is that you make a many-body system, right? You have a many-body system. This many-body system has some excitations, and then you move around these excitations. You have enough control to move around these excitations around each other. Then you can show that by an extension of the Berry phase, which you know from quantum mechanics, when these excitations change around each other, some unitary gates acts on these states. So a state psi I evolves some other states, depending on how you manage to move these excitations around, right? And it doesn't matter how you move these excitations, because all this is topological. So it doesn't matter that you make a mistake and in moving around these excitations, you make an error or you go somewhere else and you make a mistake. It's enough to make a full circle. If this circle is traversed slowly or fast or with some deviations, it doesn't matter. It's all topological. There is no error. So by moving around these excitations, you make these gates. This is called topological quantum computation. And if you have, for example, 3 qubits, if you manage to move around the first 2 qubits, you implement the gate sigma 1, for example. Sigma 1 is the Pauli gate. If you manage to move around these 2 or to intertwine these 2 qubits, you make another gate, and then you move around. For example, the sigma 1 is this one. It's a specific rotation around the z-axis with the angle of 3 pi over 10. This all can improve. For this one, you make another rotation around an axis n, which can be calculated by a number of theta. These are all details. I want just to give you the basic idea. And then, if you braid these 2 elements twice, you make a new gate, which is RZ of 6 pi over 10, and so on and so forth. If you do many more braiding, then you can have access to the full rotations on the larger set of rotations on the sphere, and more rotations, more and more braiding will enable you to do more and more gates. I'm now coming to the closing of my talk. And in this way, you can do topological quantum computation. I encourage you to study the basis of it. It's a very complex and difficult subject, but it's exciting because it's the intersection of mathematics, condensed matter physics, and quantum computation. So you will learn a lot of things about it. And finally, before closing my talk, I will tell you about the status of this field in the world, right? To have an idea how different platforms of qubits have been made by different research groups, by different companies, by different universities and research institutes. And this is the status. Qubit platforms. There are 3 categories: atoms, electron superconducting loops and controlled spins, and photons. These are the 3 main categories. With atoms, you have trapped ions, right? And cold atoms. You can trap ions in some electrostatic field with some magnetic field, of course, because with the pure electrostatic field, you cannot trap an ion. You have to do something more. This is trapped ions. You can manage to control a set of qubits, and these are the labs which do these trapped ions things, MIT, IQ, many other things, yeast and so on. The cold atoms is like putting some atoms in an optical lattice. Then you have electron superconducting loops, right? Like quantum annealing, which I told you, superconducting circuits, silicons, NB centers in diamond, and topological, which is being followed in Microsoft with lots of budget, and photons. And these are the companies. And as you see, for example, some of these companies work on all of these platforms. This is the status of qubit counts up to now. And these circles, right? If it's clear, you can read the number of qubits. For example, IBM has a quantum computer of 127 qubits. Google has 53. And Intel has 49. we get T as 13, if I'm not wrong, and so on and so forth. All of these work with superconducting quantum computers. Then optical components. This is Xanadu, 216, 113. This is the quantum dots. Then this is the trap-band quantum computers. The numbers are 12, 32, depending on the lab or the company, 24, and so on. Right? This is the status of quantum qubit counts. It's extremely difficult to add one qubit. For example, in ion traps, it's easy to, not easy, if you make, for example, 10 qubits, you trap 10 qubits, 10 ions in an ion trap. If you want to add one more qubit, you have to spend a lot of energy and time to add just this one qubit. It can take years, because when you add one qubit, the system becomes warm, and then instability develops in this system. Phonons will come and destroy it. And this is the qubit count predictions, right? With the IBM, there's a promise of, in 2013, right? There's a promise of making 1 million. I'm not responsible, of course, for these promises. Up to 2030, the promise of IBM is 1 million qubits or more. Google has a promise of 1 million. Rigetti, 4,000 million. Then, and so on and so forth. 1024 with IQ, and so on and so forth. This is the silicon quantum computer. So this is the status that companies and different labs are giving to governments, and giving to people, and giving to us. We do not know if this happens or not, but many people who are working in this field are hopeful that this will be established. Thank you very much. Yes, please.
Yeah, thank you so much for this really kind presentation. My idea is related to how can we design the material of this kind of quantum computers. So if you can give us a small idea roughly how the material part can be done. Because we are working in materials and like superconductors and so on, but the normal stuff. But I don't know how can we transfer to this quantum.
First of all, I'm not an experimentalist, so any idea that I give you is roughly.
Yeah.
Right? There are some explicit criteria, right? First of all, you have to have these are called the Vincenzo criteria. There are 5. First of all, you have to have a specific microscopic quantum system with 2 levels, and you have to be able to control these 2. So it's not enough to have a control of one atom, to put one atom here and one atom here. You have to go inside there to have control over the states of this. So you have to be able to move the atom from this state to this state, or to make a superposition of these 2 states. So, as a material engineer, you have to be able to go and control one single qubit. That's the first thing. The second thing is that these qubits should have a long decoherence time. If you prepare a qubit, for example, immediately it may collapse, depending on what kind of qubit you are making. If you have a photon, it will last for years, hours, so to say. But if you have an electron, it may decay. Or if you have an atom, it may collapse immediately. So the decoherence time should be long. Then you have to be able to make quantum gates in a very short time, so that in the decoherence time before the atom collapses, you'll be able to make many calculations. And then you have to be able to increase the number of atoms. This is called scalability. All these criteria should be met by one single platform that we have. That's why people are going around different platforms. Because one platform may be easy for one criteria. The other platform is not good for that criteria. So all of these should be met at once so that you can make a good quantum computer. To be more specific, at present, the most promising thing is superconducting quantum bits. They make these Josephson junctions. It's a small microscopic quantum circuit, LSC circuit, so that the currents goes this way or that way. This is the platform which is used by Google and IBM and so on. Yes, please.
You told why calculator results of two.
Yes, yes, please give me.
And you
Yes, I guess. I hear, but I do not understand. Yes, please.
you told results of the quantum computer is based on the probability.
Yes.
I want to ask that are there any possibility to predict the next result? I mean, should we expect Gaussian distribution between the results? Because in nature, it
Yes,
happens
I
like
can-
a.
Yes, I can use this blackboard or this whiteboard. The art of writing quantum algorithms like this one. This is the uniform superposition that you have, right? The quantum algorithm, right, should be written such that this uniform superposition evolves to this one, right? This is psi 0, psi in, this is psi out. And this is the correct answer. Right? So, the art is that you develop a wave function in this form such that when you measure the output, the probability of finding an answer which is the correct answer is high. If you, by chance, you obtain one of these wrong answers, you check that the answer is not correct, you repeat the algorithm again. But the chance is really high, if I understand your question correctly. Please?
So as quantum bits are extremely sensitive, so could we have in our near future quantum chips implemented in our devices?
In your devices, you mean?
Yeah, like I don't know if we have. Could it be accessible to us via or something?
It depends on when, right?
Like, is that technology looking positive to us?
Yes, let me tell you a story, right? And then you will find the answer. I think it was in 1965 or something like that. Then there was a conference by IBM managers. And then the director of IBM told the audience that I'm happy and pleased to tell you that this year we will have 5 orders of computers. So this year we can sell 5 computers. And the weight of these computers is below 1 ton, 1,000 kilograms. That is in 1965. And now you have in your pocket these mobile phones, which is much more powerful than those 1 ton IBM computers, right? So nobody can predict, but the story shows that technology goes in a way that your dream will become reality. But not in, for example, 10 years or 20 years, but maybe, God willing, 50 years, we will have a quantum computer in your pocket, maybe. Yes.
Can I ask something from your figure?
Yes.
Does this mean that cannot solve a problem, or quantum computer cannot solve a problem? We don't have a prediction of the result. I mean, you said we can check if the result is wrong.
No, it can solve. I showed you that it can solve problems, right? You should have the definition of the problem in precise form, right? But you do not know the solution. So the quantum algorithm should be written this way, that the probability of finding the right answer is becoming very, very high, right? Then you check the answer, like the needle in the haystack. You give me a number, a large number, I give you the factors, right? I run an algorithm. This is the, I know which number you want. I want to factorize, right? But I do not know the factor. I do not know which p is a factor of this. I run the algorithm. The algorithm is written in clever ways, so that here is one of these factors, p, right? By a high chance, I find p. But there are chances that I find an irrelevant number, like p prime. We divide n by p prime. If you find an integer, you say okay. Right? If not, you repeat the algorithm. Any more questions? So, the students are trying to ask questions. Okay. The ice melts. Shall we stop? Okay, we can talk after. Thank you very much.